Hi, and welcome to the third video in a series about differential forms. In the last video, we looked at this idea of specifying a k-tensor based on how it acts on k-tuples of basis elements in a given vector space. This is an important idea and a generalization of how we can characterize or specify linear transformations by how they act on a given basis for a space. So a lot of the content that we covered in the last video was fairly abstract in nature, and looking back on it, it was quite heavy for one video. So in this video, I would like to actually explain a subsequent example that's given, and hopefully this will elucidate the ideas of k-tensors and expressing things in terms of components. So general k-tensors on R to the n, so n-dimensional real space, Euclidean space. So let's write out our example. So we let V, our vector space, simply equal Euclidean n space. And we let, as the usual convention goes, E1 through En be its basis. It's a standard basis. Which has 1 in the ith slot and then 0 in all of the others. This is the standard basis. And then we denote, we saw the construction of the dual basis, so L1 of V. So we let phi, this corresponding dual basis, phi1 through phi n, be the dual basis, and in parentheses for L1 of phi equals L1 of R to the n. All right, so we have n of these basis elements or basis functionals. If x is a vector in Rn, so if and I sometimes do this notation where I denote vectors as having a line underneath. Sometimes you'll see the arrow above, but for some reason I've adopted this convention and I've just been using it like that. So if x is a vector in R to the n has components, components, let's say x1 through xn, that is, x can be expressed as the product and the sum over these basis vectors as such, e to the n, so like this, we're splitting it up. We have phi sub I of x, which equals phi of x1 e1 plus all the way through xn e sub n. And this just equals x sub I. Hence, phi sub I from R to the n to R describes projection, projection meaning restriction to a certain component, projection onto the ith component or factor. Okay. So this is the case where we had k equals 1, as we've been looking at the dual space in the simplest case, and now we want to look at this general case where we don't have just one index to look at, but as we saw, capital I to denote these k-tuples of indices in general. So in general, given I equals this I sub 1 through I sub k, phi sub I satisfies, and now phi sub big I, because now we're specifying on a whole k-tuple, and I really don't know why I just omitted without a description of what it's acting on, but x1 through xk is going to satisfy phi I1 x1 through phi ik xk, right? So it equals this product over here. In product notation, and sorry, this is not a product. This should be written like this through commas, and I've not been doing a totally comprehensive job of specifying when something is a product or a list, but this is taking in k arguments, which we should expect because it's a k-tensor, and this is a product on the right-hand side. So this is going to be equal to, as we saw in the last video, let's say j equals 1, and it goes till k. So we have phi I sub j x to the jth component. So this is exactly analogous to, yes, over here, except now we're taking vectors v, we put in an arbitrary vector space v, but now for v equals r to the n, we're just denoting vectors by x and splitting it up into its constituent parts, so x sub j. Okay. Let us write this big X now equals this kind of row vector of component parts. So x1 through xk corresponding to some little x, which can be expressed as we saw above. And we let x sub ij, so xij as indices, denote the entry of x in row I and column j, just as matrices are referred to or indexed. Right, and we see that this is in fact is going to be how we refer to this, because this is going to be a matrix where its columns are going to be written as these component vectors of x, right? So we have x sub 1 e1 plus so on through xn en, where each of these are vectors, column vectors, and now we have these expressed in rows. So this is just a matrix. So this is going to be, we have k columns and we have n rows. So we have an n by k matrix here. So x is n by k. And x sub j is the vector having components, xj1, 1j through xnj. And in this notation, as we've described over here, we have phi sub big I of x1 through xk being these projections, which equals now this product, which we have simplified the notation for. So I11, x, I22, and this is one index, this is another. Sorry, I should be more clear again with that. X, I, k, and then k. So this is our phi sub big I. And we notice here that this is just a product of k variables. And really what it's going to be is a monomial. So it's a single term because it's just one product. It's a monomial in the components of the vectors x sub 1 through x sub k. So it's expressing this product in that form. The general k-tensor now on r to the n is just going to be linear combinations of these monomials. So we just have these kinds of products of terms in the x1 through xk vector components, and we take sums of those as multinomials. And now we look at the general form of a k-tensor on n. General form of a k-tensor on r to the n. When k equals 1, we're looking at 1 tensors. F of x is going to equal, for some scalars, d1 through dn. Right, linear combination here. For some scalars, x sub, no, sorry, not x, so d sub I, let's say, in R. Right, so this is the form of a general one tensor because you're breaking it up into these components. So products of scalars times singular component of vectors, and you just have them all broken up into n discrete parts, basically. We'll see how this kind of collation or combinations in terms of sums and products of more than one variable is going to now change the form of k-tensors where k is greater than 1, because let's take the general 2 tensor on Rn. Let's say when k equals 2, we're looking at 2 tensors. We have, let's say now, g, and let's express it in terms of x, y, as the general Euclidean convention goes. It'll equal now sums of the form, whereas we could write this as maybe a sum over, let's say, I is a safe index to use now. I equals 1 to n di xi. Now we have scalars that are going to be indexed in the k equals 2 case by 2 indices. And we're going to have xi just as one term, and we're going to have the sum go over another y vector. So now instead of this, we have the general 2 tensor form given by, that's not great sum notation. We have ij being 2 indices equal 1, and they run to n both. Dij being these scalars, x sub I, y sub j. This is the general form of a 2 tensor. We'll look at when k equals 3, just to give you a sense of that pattern now. We have 3 tensors on Rn. We have, let's say, h now x, y, z. I'll omit the underlining because I think it's clear that we're just taking over vectors. We have I, j, k equals 1, runs through n, d, I, j, k for the scalars that are being indexed. And now we have x sub I, y sub j, z sub k. Actually, k I shouldn't use, so maybe L is fine now. Let's just use L. Okay. So now you get a sense of the general form of a k-tensor on Rn, where the sum is what's going to n, and you just take when the dimension increases of the tensor over successive indices, right? So you have scalars indexed by this form, and then you have products of your vectors indexed xi, yj, zl as follows. So this generalizes, and so on, right? So hopefully this was a clear example, not super long or super exhaustive, just showing how our previous concepts tie into when v equals Rn, so Euclidean n space, and this idea of tensors. And now in the next video, we're going to introduce the tensor product, so please stick around for that, and I will see you then. Thank you.